Good morning, class. This is lecture 6 of AREC 333. Today we will continue with the economic aspect of production and from the input perspective. Last lecture, we started this topic and we introduced some basic concepts, both the value concepts, TVP, MVP, AVP. Those concepts actually correspond to TPP, APP, MPP. But TPP, APP, and MPP, those are physical concepts. And in the economic aspect, we use, for the input side, we use the value concepts. And then we also covered the cost concepts, which are the TFC, total factor costs, and marginal factor costs. And we just started with the economic regions of the three stages. And we mentioned that stage 3 is not economical. And I also started saying that stage 1 is also not economical, only stage 2 is economical, but I didn't explain why. So part of today's objective is to explain why it is not optimal to produce in stage 1 and at exactly what point in stage 2 that the producer can reach maximum profit. After we're done with explaining why stage 1 is also not economical, we will move on to profit maximization in stage 2. And as you can see from this outline, there are actually 3 optimality conditions. We explained that here MFC equals to MVP. This one is actually the first order condition that we covered in lab session 1. And after this lecture, if you cannot follow why we need the first order condition, then you probably need to go over the recording of lab 1. And the second one is second order condition, which we also covered in lab 1. And the third condition here is actually nil. So this condition is make sure that the short run profit is positive. So TVP is greater than the total variable costs. And if the profit is negative, then the producer will just not apply any input and produce 0 output. That is better than getting a negative profit. So those are actually the 3 conditions of profit maximization in stage 2. And if you met all those 3 conditions, you can actually find the specific point where the producer will get maximized profit. And once we're done with those profit maximization conditions, and if there's still time, then we will look at several cases where the input price and output price changes. Why does that matter? Because at which point the profit is maximized actually depending on input price and output price. And if we have time, we will introduce some real world examples of those price changes. And hopefully you don't feel like this course is far from real life, and you will see some of the concepts or principles that you learn from this course is actually relevant for real world. Readings for this lecture include the Birding chapter 3, Rasmussen 3.1 and 3.2. If you have the BD et al. Book, then I would also recommend 3.18 to 3.1c. So both Rasmussen and BD et al. Are a little bit above the level of this course, but if you're really interested in the topic, you can read those 2 textbooks. It will help understand the concepts introduced in this course much better. I explained this in previous lecture that the difference between input perspective and output perspective is that when we're solving the profit maximization problem from input perspective, all of the costs and the value of output, they are all functions of input. And here input is the choice variables. So if the producer want to reach maximum profit, the producer will get there by adjusting the input use. Later on, when we have profit maximization from output, then you will see total revenue and total cost will be function of output, and there the producer will decide how much to produce, like the quantity of the output. Just to give you a recap, we already showed this in last lecture, but profit here, pi, is defined as a difference between total value of product and total factor cost. So both TVP and TFC are functions of X, which is input. And I showed you guys that profit here is just the difference between the pink curve, which is a TVP curve, and the blue line, which is a TVC curve, because this is a short run case. So we're looking at total variable cost, and fixed cost is not affecting the producer's decision. And to help you better understand why how we can find the maximum profit, I actually plot the difference of those two curves as the black line, black curve here, which is a profit curve. We stopped here last time explaining why stage 3 was not economical, and then for stage 1 there are several cases we need to consider, and we discussed case 1, which is the price of the input is equal to 9, so R is the price of the input. So in that case, the profit is equal to 0, and input use is exactly X2. And we also explained that for case 2, which is R is greater than 9, then TVC curve will move further, will move higher and higher above the TVP curve. And if that's the case, then the profit will be negative, which explain why it's not economical to produce under that case. And then there will be another case, which is what if the input price is smaller than 9 or lower than 9, then the TVC curve will be below TVP curve, and there could be positive profits in stage 1, and it is a little bit more complicated, and I will explain it to you in the animation. Okay, so let's look at the case where the input price is smaller than 9. So if the input price becomes smaller, you can see that the TVC curve is gonna be below TVP curve for part of it. And if I further reduce it, then you can see it is getting, TVC is getting smaller and smaller. And if you pay attention to the profits, you can see that for some region in stage 1, there's actually positive profit. But why do we say that it's not economical to produce in stage 1? The reason is because the maximum profit is not reached. And we're gonna actually look at stage 1 for 2 regions separately. The first region is the region to the left of X1. So why do we look at the region? Is because in the region MVP is increasing. So if the rate of the value of your output, rate of change of TVP, which is the rate of change of the value of your output, is increasing, and your TVC, the rate of change is constant, which is the input price. And to the left of X1, if you increase your input use by a little bit, then your TVP will increase at a faster rate than your TVC, and you can increase your profit. So to the left of X1, you will never get you can always increase your profits by increase your input yields. So it's not economical to produce to the left of X1. That is actually a little bit easier to understand. However, it is not easy to understand why it is also not economical to produce between X1 and X2. So some might argue that at that region, the MVP is decreasing. So the rate of change of your TVP is decreasing. So maybe I can start producing in that region. But that's actually not the case. Why is that? It's because still what you should really pay attention in stage 1 is the MVP and MFC curve. So between X1 and X2, you can see although MVP is decreasing, however, it is always above MFC curve. So no matter how I change the input price, as long as input price is smaller than 9, then you can notice the MFC curve is always below MVP curve in that region between X1 and X2. And if that's the case, even MVP is decreasing, it's still above MFC. And if that's the case, then again, the rate of change of TVP is still faster than TVC. So in that region, even MVP is decreasing, you can still increase your profit by increase your output yields. So again, it is possible to get positive profit in this region between X1 and X2, but you can always get a higher profit by increase your input yields. And if you pay attention to here, this point where the profit is maximized, and if I change input price, you can notice that point is changing, but that point is never to the left of X2. So pay attention here. Even if I'm changing my input price, the maximum profit is never reached to the left of X2, and it is exactly at the input price equal to 9 that the profit is equal to 0. You might wonder, there's another point here on this region that it actually also satisfies the condition that the first derivative of this profits is equal to 0. But this is actually the minimum profit point. So we're not interested in this point. We're interested in this point where the profit is maximized. So never optimal to produce to the left of X2 is because MVP is always above MFC, and you can always increase your output by increase your input yields. So and another thing to notice here is that the maximum profit, if you notice this point, you will notice that the input yields for maximum profit is actually where the MVP and MFC intersect. So pay attention to that, and that's no coincidence, and we will explain why that's the case. Let's look at the MFC, AVP, and MVP curves. The relationship between them when I'm adjusting the input price can also explain why it is not economical to produce in both stage 3 and stage 1. So first, this is the case where R is equal to 9, and we can find that when this is the price where our MFC curve, which is this horizontal curve here, actually intersect with MVP and AVP. So these three curves intersect at this point. And if you still remembers the definition of AVP, it is actually TVP over X. So the region actually surrounded by this origin X2, D, and this point. So this region is actually your TVP. And the region, again, below the MFC. So because MFC is actually also equals to the average factor cost. So X2 times MFC is also the total factor cost. And the difference between AVP minus MFC, and if you multiply that difference by X2, that is actually going to be the profit. So at this specific point, because AVP and MFC are the same, so the profit will be 0. If I increase the input price, you can say MFC is above AVP curve. And because MFC is actually higher than AVP, then the region between the several points, MP, this KL, so MPKL, that region is actually the profit loss. So if you get a higher input price, then if you produce to the left of X2, you get a negative profit. And if the profit is lower than 9, then you can notice AVP is above MFC, and this region TNLK, that region is actually is positive. So now it got a positive profit. However, you can see here, if you're producing to the left of X2, then your profit for this region is actually smaller than the profit if you can produce at this input. The profit will be KL and P, the area of that rectangular. So it's not optimal to produce to the left of X2, because if you increase your input use, then you can always get a higher profit. The region of that rectangular will be bigger. That rectangular represents the profit. So between this X2 and X3, this is a stage 2. Where exactly can we get maximum profit? That is actually we need several conditions. The conclusion that stage 1 is not economical is because the maximum profit is not reached, and that is actually based on an assumption that the producer has unlimited funds. And that means, for example, if R is equal to 5.9, the maximum profit will be reached at this point. And the assumption here is actually the producer can afford this input use. So the money that the producer need to buy this input will be 5.9 times the level of X here. However, if for some reason the producer cannot afford this much of input use, for example, the producer can only afford X4 here, then we can say that stage 1 is actually economical for that producer with limited funds, is because at X4, you can see that the producer can still get positive profits. So here, this is a profit curve, so there's positive profit, and if this is the maximum input the producer can afford, then this will be the maximum profit that the producer can get with limited funds. If X4, if we assume that there's another producer with even more restricted access to to fund, and now that producer can only afford X4, which is to the left of X1, and we can say under this input price, the profit is still positive, so this producer can still produce at X4 in stage 1. However, if the input price further increase, for example, here, we can notice that at X4, the profit is actually negative. So if the input price is equal to 8.2 and the producer can only afford X4, then it is better for that producer to shut down, to not produce at all. And it's because only to the right of this input use, then the producer can get positive profit. So I do want you to keep in your mind that positive profit is another constraint, which is not mentioned in the lab session for finding maximum profit. So this is actually an extra condition for when we're doing the economic analysis in addition to the mathematical restrictions. So to summarize, it's not economical to produce in stage 3. It's because TVP is decreasing if you increase your input use, and TFC is increasing. So in that region, you will your profit will decrease. And it is also not economical to produce in stage 1 if we assume that producer has unlimited funds, and in that case, the reason for not to produce in stage 1 is not because of negative profit. There's possibility that there's positive profit in stage 1. However, the maximum profit is never reached if we assume that the producer has unlimited funds. So in stage 1, you can always increase your profit by increase your input use. And stage 2, which is between X2 and X3, which is the economic region for a competitive firm with unlimited funds. And that's going to be the objective for the rest of today's lecture, is find out exactly which point between X2 and X3 the producer can maximize profit. The input level that maximize profit in stage 2. So in this graph, if you pay attention, you will notice there is a pink line, which I actually write the equation for that line. That is the tangent line of TVP at this point. And that, like the slope of the tangent line is actually the value of your MVP. So MVP at this point should be 5.2, and the slope of this line is also 5.2. And there's also another 5.2 here, which is an input price. So first, what is the profit? Because we want to maximize profit. So profit is the vertical difference between TVP and TVC. So we want to find the input use where the difference between TVP and TVC is the largest. And when can you get that biggest difference or largest difference is when the tangent line of TVP, which is this line, is when the slope of this tangent line is equal to the slope of your TVC. So when those two slopes are the same, then your profit is maximized. So I do want you to remember this, which is profit is maximized, or the difference between TVC and TVP is the max when the slope of TVP, or the slope of the tangent line of TVP, is equal to the slope of TFC.
And if we translate that to the relationship between MVP and MFC, it is actually MVP equals MFC. So again, profit is maximized when MVP is equal to MFC, and also when the slope of TVP is equal to the slope of MFC. So how does this related to the conditions that we mentioned in the lab session? So remember, in the lab session, we said if we want to find maximum or minimum point of a curve, the first thing is that we need to find out at the point on the curve where the first derivative is equal to 0. So if we go back here, the profit is equal to TVP minus TVC, and the first derivative, which is equal to TVP minus TVC prime. And remember, remember we learned in the lab session that if you have sums and differences, the derivative of the sums and differences is just the difference of the original function. So here the pi prime will equal to TVP prime minus TVC prime, which will equal to MVP minus MFC. So if we want to find out a maximum or minimum point of a function, we have to set the first derivative equal to 0. So if we set this equal to 0, we can find the condition is MVP equals MFC. So that is the first condition. And again, this condition of setting the first derivative equal to 0 is only the first step. And actually, let me remind you here something in case later on in the output, when we're doing profit maximization from the output side, there's something you need to pay attention. Is when we are doing maximization from input, the input X here is a choice variable. So the producer is reaching maximum profit by adjusting X. So for whatever is the choice variable, then we're taking derivative of profit with respect to that choice variable. So the choice variable for the input side is X, but later on, if we are solving the profit maximization from the output side, then the producer is adjusting the level of outputs to reach maximum profit. Then by at that point, you should put Y at the bottom here. So you should take derivative of Y respect to X. So you need to pay attention every time what is your choice variable when you're taking the first derivative.
So the first condition for profit maximization is what we call first order necessary condition for unconstrained profit maximization, which is MVP equals to MFC. And why is that? Is because we set the first derivative of pi, or the first derivative of profit with respect to input, which is a choice variable, equal to 0, and we get this condition. And the reason here we call it necessary condition, not necessary and sufficient condition, is because just this condition itself, we cannot be sure whether we are getting a maximum or minimum profit. And we actually need more condition that we can be sure that we find the input level that will maximize profit.
There are two things that I want to show you here about the geometry of this condition MFC equals MVP. So you should put your attention here of this point. So if I'm adjusting my input price, and you can notice that this point is associated with a point of profit, maximized profit. So if I'm changing my input use, and you will notice that the point where the profit is maximized, we always find that this is a point where MVP and MFC intersect. So MVP equals to MFC is always satisfied whenever we have the profit maximization. And another point that I want you to pay attention here is that if I'm adjusting my input prices, you can find that the maximum profit is always between X2 and X3, and it's never to the left of X2. So again, this is another demonstration that stage 2 is the economic region. However, as we mentioned in lab session, the first order condition itself is not enough to tell whether we find a point where profit is maximized or minimized. That's why it is called the necessary condition, not necessary and sufficient condition. So we actually need the second order condition to tell whether we find a point where profit is maximized. So this is where the graph, if you actually only use the first condition, which is MFC equals to MVP, and you can notice like this is a point I have just showed you that MFC is MVP. If you pay attention to the first stage, you will notice there's another point here which also satisfies the condition that MFC equals to MVP. But at that point, because we plotted the profit curve here, and we are able to tell that this is a minimum profit point, and this is a maximum profit point. However, imagine that you don't have this graph, and you're only if you only have the algebraic function, and you use this condition, this first order condition, to find out the maximum profit, then you might end up find this point where profit is minimized, not maximized. So we need the second order condition to find out whether it's this point or it is this point. So between those points, which one should we choose that will give us a maximized profit? So this is from your lab 1, and we say that if this is max here, then we have the condition that the second order derivative is smaller than 0, and if this is a mean here, then we have the second order derivative is greater than 0. We can actually try to plot the first derivative of these two curves so that you will understand better. So here we have at this point, the first derivative is equal to 0. And for this function to the left, from here to here, we have the function is increasing. So so we have the first derivative is greater than 0. And for this region, the first derivative is smaller than 0 because the function is decreasing. So this relationship of increasing, decreasing, and the first derivative I already showed you in previous lectures. So if we have the first derivative greater than 0 and it reaches 0 at this point, and then after this point it's smaller than 0, then our first derivative might be something like this. So that's the first derivative function, and that's a function of y prime. And if that's the first derivative, and we take a derivative of this function again, So the derivative of this function, and what are you expecting? So we can say that for the whole region from here to the right, then this is a decreasing function. So if this y prime is a decreasing function, that means the derivative of y prime is smaller than 0. And this is y double prime, and that is the second order derivative. So that's why when you have your second order derivative smaller than 0, you can make sure that here it is a maximum. And it's similar for this function on the right, that if the second order derivative is greater than 0, then we can be sure this is a minimization point. Once we are good with the first order and second order conditions, then we can get back to this profit curve here. And using the first order condition, which is d pi over dx equal to 0, from that we can derive MVP equals to MFC. And using this first order condition, we can find that at this point and this point, those 2 points both satisfy this first order condition. And now we need to use the second order condition to tell which one is actually a maximum point. And this profit curve actually have the 2 shapes that we mentioned in previous slides. This one is concave upward, and this one is concave downward. And for the one on the left, you have a minimum, and this one, the second order condition is greater than 0, and this one you have a maximum, and the second order condition is smaller than 0. So this point here is this shape, and this one is this shape. So then if we get our first order condition and we further calculate the second order condition, and we can, after we have the second order condition, we can actually find out that at this point, the second order condition is greater than 0. We can say, oh, that's a minimum, not a maximum. And at this point, we actually have the second order condition smaller than 0, and this is truly a max profit, and that is what we are interested, the maximum profit. And in this graph, you can actually find out that since both stage 1, which is to the left of x2, and stage 3, which is to the right of x3, those are both not economical. The only economical region is stage 2. And stage 2, you can find out that for the MVP curve, it's downward sloping. And although we use this example of the typical production example, and the shape is this curve here, this TVP curve, this shape, it has all 3 stages, but in real world, a lot of times we only use production function that only have this region, this downward sloping MPP or MVP region. And a lot of cases you don't say MVP especially have this part to the left where MVP is increasing. You also don't say this part to the right where MVP is smaller than 0, and usually you will say downward sloping MVP, and that's most of the case where we're interested to find out the maximum profit. Okay, let's summarize the optimality conditions, and by optimality here I mean profit maximization. Both maximization and minimization belongs to optimization. So there are actually 3 conditions in total to make sure we get a maximized profit. So the first two conditions are actually, I will classify them as those mass conditions. Is if I give you a production function and I give you the output price and the input price, then you will be able to find out the profit. And since this is from the input side, your profit will be a function of your input. And once you have this profit function, you can use the first two conditions to make sure that you will find a maximum profit. So the first one we spent quite some time explaining is MVP equals to MFC, and how we get this condition is we set the first derivative of pi with respect to x equal to 0, and once you solve this condition, you will get MVP equal to MFC. And that what does this condition mean? It means that the marginal value of your product is equal to your, the marginal factor cost. So it is at that point that you will get either max or mean profit. So again, the first order condition is only a necessary condition, not a necessary and sufficient condition. By solving this condition, you can get a max or mean. And in the previous graph, we showed there are actually 2 points there. One is for max profit, the other is for minimum profit. And we actually need another condition, the second order condition, to make sure that we find the max, not the mean. So how do we find this? So after you solve the first order condition, you usually should be able to get 1 or 2 or maybe later on more x values. And what you should do is that you should actually calculate the second derivative of pi with respect to x, and then there you will check that the second order condition is smaller than 0, and if it's smaller than 0, then you get a maximum profit. And if it's greater than 0, that means you get a minimum profit, not maximum profit. Oh, there's a typo here. So pi double prime should equal to MVP prime minus MFC prime. So that's the second order condition. And usually the first two conditions will make sure you get a maximum profit. However, these first two conditions didn't exclude the case where you could get a negative profit. So there's actually another condition. It's called total condition in production economics, but this condition is basically asking after you solve the first two conditions, you have to check, or you have to, for example, after the first and the second order condition, you find the optimal input use level, and then you should actually check or check the value of pi evaluated at that input use to make sure this is positive, because economically, if profit is smaller than 0, then the producer will just shut down, and that in that case your profit is equal to 0. So if you from the first two conditions, you find out that your profit is smaller than 0, then you shouldn't use this point as a point of profit, maximized profit, and your really profit should be equal to 0. Well, where the producer will choose x star equal to 0, will not use any input, and then the output will also equal to 0. So in your MFC, MVP, and AVP curve. This means the AVP curve is above the MFC curve. So why is this? It's basically TVP over X is your AVP, and TVC over X is generally MFC if you assume the total variable cost is equal to the price of the input times the quantity of the input used, then this input price will equal to your MFC. And if you actually write it this way, you can also call it average variable cost. So that's why we get the third condition here. So this is more rigorous. If you do check all three conditions, you will find a maximized profit. And as I mentioned before, in this course, most of the case, when you solve the first order condition, you will find there's only one point which satisfy this MVP equals to MFC condition. And usually the function I give you, it's already indicated that it will be a maximized profit point. However, it's a good habit to check the second derivative. And if you do find there's 2 points which satisfy the first order condition, then you definitely should check the second order condition. The 3 conditions for profit maximization mentioned in previous slide are more general conditions like MFC equals to MVP and second derivative smaller than 0, you get positive profit. All of those conditions actually apply to both perfect competition market and imperfect competition. And if we further assume that the output market and the factor market are both under perfect competition, then our optimality condition can actually get simplified. So remember that pi, which is a profit, is equal to TVP, which is the total value of your output, minus your total factor cost. And total factor costs have 2 components. Rx is the variable cost and B is the fixed cost. So TVP minus TFC is the general term. If we assume there's perfect competition in output market, then this is the output price P. It doesn't depend on X. It's a constant here. So if P is a constant, then later on when we derive the first order condition, the optimality condition is much easier. Again, also in the factor market, this is input of this is the price of the input, and if we also assume perfect competition in factor market, then we also have this linear relationship where R is a constant and does not depend on X. If R also depends on X, then if you remember from the lab session, then we need to use the product rule to calculate the derivative. However, if R is a constant, then when we are calculating the derivative of Rx with respect to X, it's just R, so it's much easier. I'll stop here today, and next lecture we will continue with the profit maximization condition under competitive markets, and I will show you what's simplified condition. You can actually see it from this slide, but I will show you in more detail how you get to that condition and what does that what's the implication of that condition.